Hi everyone, and welcome to our third video on the type binding model and explaining band structures to chemists. In our previous two videos, we talked about the origin of band structure and how they arise from combining multiple orbitals together in an infinite array of atoms in a crystal. And in the second video, we talked about having the differences between having s-like orbitals and p orbitals, and how to determine by symmetry whether a band should run up or run down as we increase the crystal momentum or the wave vector k. Now in this video, we're going to talk about what happens when we want to have more than one orbital per atom. Okay. All right, so like I said in the previous video, we looked at a chain of chain of atoms with s orbitals, which is shown in the lower left, and a chain of p orbitals, a one-dimensional chain of p orbitals shown in the lower right. And we saw that the band structures for these two systems were very different. They both gave cosine bands, right? So the bands looked like cosine functions as we go from zero momentum to momentum equal to pi over a. But they were fundamentally different. The s orbitals increased in energy as we increased their momentum. And the p orbitals, it depended on what type of symmetry we had. If we had orbitals that combine out of phase between their nearest neighbors, like the px orbitals, then it went down in energy as we increased crystal momentum. And if the orbitals added constructively together with their nearest neighbors, like a py or pz orbital, then their dispersion looked like the s orbitals. Okay? But our question for today is, what happens if we allow our wave function to comprise of multiple orbitals on each atom? Well, the answer to that is we're still going to need a Bloch wave function. This is a wave function that's going to obey Bloch's theorem by construction. And so we're going to have our wave function psi of x still going to be parameterized by some wave vector k. It's going to look like a plane wave, e to the I kx, times a sum of orbitals all centered at the same spot in the Brion zone. But now we're going to have I orbitals. So we might have I is equal to 1, 2, 3, 4, etc. And we're going to have varying amounts of those orbitals in our wave function. So we're going to write that as some complex coefficient c sub I times phi sub I. All right, so that's the general formula. In this video, we're going to show explicitly what happens when we just have two orbitals per unit cell. So we're going to make a very simple system. And in fact, we're going to look at just s orbitals and px orbitals. And so I'm going to write our Bloch wave function psi of k as this plane wave, right? Sum over the sum of these plane wave phase factors. The sum over n, where n is an individual lattice cell, so how many translations away from the origin we are, e to the I k n times a, where a is the lattice constant, times c sub s, our coefficient for the s orbital located on the atom at the origin, plus coefficient c sub p, so how much p orbital we're going to have. And these are going to be px orbitals and s orbitals. The only two types of orbitals we're going to have. All right, so just to go over that one more time, we have our Bloch wave function for an s and a px orbital, and we're going to have an infinite linear chain of these. And so we have our Bloch plane wave portion of the wave function. That hasn't changed from when we only have one orbital per unit cell. We have our s orbitals, phi sub s and phi sub p. And then we have these coefficients. These are the amplitude coefficients for how much s orbital and p orbital we have in our wave function. If we assume that our orbitals are orthonormal, so they don't overlap with each other, we only have two of them, and we have a normalized wave function, then the magnitude of c sub s and the magnitude of c sub p squared have to sum up to be equal to 1, right? We can't have, our wave function has to comprise only s and p orbitals. Now, two things that we want to be aware of. One, c sub s and c sub b can both be complex. They're amplitude coefficients, so there's nothing that says they have to be real. And two, these are now functions of k. So at each different point in k, our c sub s and our c sub p values can vary. And what we want to do is we want to find, so we have these different possibilities. We have an infinite number of possibilities, right? We can have an infinite number of wave functions. We have any value for c sub s and c sub p, so long as their magnitude squared adds up to 1. which ones are we going to have in our unit cell? What's going to be our actual wave function? Well, to get that, we're going to use the same variational method that you used when you took physical chemistry and you looked at MO theory. You looked at molecular orbitals. We're going to use the variational method. And so what we're going to do is we're going to calculate the average value for our energy, the average value of our Hamiltonian. And then we're going to find the coefficient C sub S and C sub P, which minimize that total energy. Okay, so let's take a look at this. Another way of saying that is we're going to find the eigenvalues and the eigenvectors. Okay. All right, so we're going to map out a strategy here. Number one, we're going to allow our chain of atoms to have both s and px orbitals. What that means is we're going to construct our block wave function as we did on the previous slide. Now we're going to act within the tight binding approximation. So we're going to let our Hamiltonian, which we're going to write as the sum of atomic Hamiltonians centered at each unit cell. We're going to let that operator act on our wave function, and it's going to couple orbitals from one atom to its nearest neighbor. So if you have an atom in the origin, it's going to couple to one behind it and one in front of it. And that's going to allow it to mix the s and the px orbitals with the atom in front and the atom behind. So we can write that mathematically. We have our Hamiltonian operator. If it acts on C sub s, phi sub s, then we're going to get C sub s. It's going to factor out, right, because that's just a number. Okay. And now it's going to be equal to the energy of the s orbital minus T sub s, the transfer integral. How much is it going to transfer onto the s orbitals in front and behind, minus TSP, which is going to be our transfer integral. It's going to mix an s orbital with a px orbital in front or behind, times the p orbital. So this is going to mean that we have our s orbital. When the Hamiltonian acts on it, it's going to turn some of that into a p orbital in front and some of it into a p orbital behind. We can do the same thing when our Hamiltonian acts on our p orbital. It's going to give us the energy of the p orbital times the p orbital minus the transfer integral, putting some of it in front, minus the transfer integral, putting some of it behind on the p orbitals, and a little bit that's going to mix the p orbital on our atom with an s orbital in front and an s orbital behind. Okay. Couple of things to note about this. First, our Hamiltonian does not couple an s orbital located on one atom with a px orbital located at the same point. We are assuming that our phi's, our orbitals, are eigenfunctions of the on-site Hamiltonian. Okay? So that they're orthonormal. They're orthogonal to each other. Our Hamiltonian does not mix them. Also, in this case, S and Px have different inversion symmetries, and H is inversion symmetric, so it can't actually mix them on the same orbital. Right, so we have symmetry constraints that prevent the s and the px orbital from mixing, given our atomic Hamiltonian. Okay, different ways of saying the same thing. And now, once we have what happens to our wave function when we multiply it by our Hamiltonian, we're going to project that onto an s orbital at the origin, and we're going to project that onto a p orbital at the origin. All right, so we're going to start from the Schrodinger equation. We have h psi equals e psi, and now we're going to project from the left-hand side phi sub s onto that. Okay. Well, that has to be equal to c sub s times the energy, right? Because phi sub s times psi sub k, remember we're going to assume that all of our orbitals by themselves are orthonormal to each other. In other words, we're ignoring the overlap integrals. And so when we multiply phi sub s and project that onto our wave function, it only pulls out phi sub s. Okay? And of course, we have c sub s amount in there, and so we get a c sub s as well. Okay. So now let's go back and look at the left-hand side of that. Oh, sorry, we can do the same thing with the p orbitals. Now let's look at the left-hand side of that equation. If I project phi sub s onto the Hamiltonian acting on our wave function, I get the following little mathematical mess. I get our wave function, our phi sub s acting on the Hamiltonian. We're going to get non-zero terms for all of these. Right? Actually, no, we're not going to get a non-zero term here. Sorry. But we're going to have to understand how that phi sub s works on the Hamiltonian acting on the atom that's on site, so that atom at the origin, plus the atom in front and the atom behind. right? And when we do that, right, when we go back and we look at the previous slide, we get those transfer integrals, and we get the following. We get that phi sub s acting on the Hamiltonian times our wave function gives us our coefficient of s times the energy of an s orbital, minus our coefficient times the transfer integral times e to the minus IKA, so that's that phase factor for moving back one atom, minus c sub s, t sub s, e to the IKA, so that's moving forward one atom, staying on our s orbital, minus c sub p, t sub sp, e to the minus ikx, so again, that phase factor that's moving us back one orbital, and the transfer integral that mixes the s and the px orbital from an atom and its neighbor behind it. And then here, this is an important thing to note, plus c sub p times the transfer integral to the p sub x orbital in front of it. Okay, so I want to point something out. Why do we have a minus sign in one spot and a positive sign in the other? That has to do with how these orbitals interfere, how these orbitals add together. All right, so what I've drawn here is an s orbital at the origin and a px orbital one atom behind. And when we look at these and how they overlap, right, they add net constructively, right? We have the same sign of the orbital, right? The px orbital has two lobes, a positive lobe and a negative lobe. And for the px orbital one atom behind, the parts of the px orbital and the s orbital of the origin, they overlap constructively. They add together in phase. And so we get a negative energy reduction. If we look at how that same px orbital adds to the s orbital, if we were just to translate it by 2 unit cells and move it to 1 in front of the atom at the origin, right, we get destructive interference. Now that atom at the origin is interacting with the other lobe of the px orbital. And so it's going to have the same magnitude of the transfer integral, but it's going to change signs. Right? So we get minus cp t e to the I minus ika for this version. And when we move forward, we change the sign of our transfer integral. Right? So we get destructive interference. In other words, we make an extra node moving forward and no node moving backwards. Okay? So that's why we have those two different signs. We can use Euler's theorem to take those e to the IKAs and turn them into sines and cosines. And when we do that and we project onto the s orbital and the p orbital, we get two linear equations. And they're shown down here. And they're linear equations with two different coefficients, c sub s and c sub p. Okay. Two linear equations. We have different ways that we can solve this, but the general way that we want to solve this is to make a matrix out of these. And so we can now define our average Hamiltonian, h of k, as the following matrix. The amount that's all, for each one of these, we're going to look at the amount of, we're going to look at the amount of c sub s that we have. Right? So this will be the energy of the s orbital minus 2 times the transfer integral times cosine k. This is just the band structure of the s orbital, plus the amount that we're projecting onto the p orbital. Right? And so this comes down here in this this matrix element. Right? So this is c sub p. This is all how much we're getting from c sub s. And then we have how much, this should be this one down here, right? So we have c sub p. And then we can look at the second column vector, and this is the same thing, but now we're looking at how much it projects onto the p orbitals. Okay? So the energies that, what we now need to know is what values of c sub s and c sub p minimize our energy, or in other words, we need to find the eigenvalues for this matrix as a function of different k's, and that will give us our band structure. And if we look at the eigenvectors, we'll be able to construct our wave functions. Okay. All right. Couple of things. This band structure depends on 5 parameters: the energy of the s orbitals, the transfer integral between the s orbitals, the energy of the p orbitals, the transfer integrals between the p orbitals, and then the amount that the p orbitals and the s orbitals between nearest neighbors will mix. So that TSP, that transfer integral between the s and the p orbitals. Right? So I've written it as 5 parameters. Of course, energy is a floating number, so it really only depends on 4, the energy difference between the ES and the EP orbitals, plus the 3 transfer integrals. to calculate those or to figure those out, we can't get that from the tight binding calculation. You would either need to look at experiments, so maybe look at some photo emission data and fit this Hamiltonian to photo emission data, or do an actual electronic structure calculation, maybe DFT or Hartree-Fock, and maybe some correlated wave function theory. But we can't get that from the tight binding approximation. But once we have those numbers, we can do all of the essential physics to understand the band structure by using these simple tight binding models. Okay, so for real systems, you need to do a little bit more work. But to just understand band structures, all we need are those numbers. Okay, so we have another thing to know is that we have two orbitals in, right, an s and a px orbital in each unit cell. That's going to give us two different bands. Right? We have a 2x2 matrix that's going to have two eigenvalues and two sets of eigenvectors. So we get two eigenvalues, that's two band energies versus k. If we had more orbitals, let's say we had n orbitals, we'd get n bands, or n eigenvalues and n sets of eigenvectors. All right. And at this point, each band can hold up to 2 electrons. We haven't talked about spin at all, so each band can hold up to 2 electrons. All right, so let's talk about how the eigenvalues and the eigenvectors of this look as a function of some of these parameters. So what we're going to do now is let's take the simplest case, which is that the s orbitals on one atom and the px orbital on its neighbor don't mix at all. So TSP is equal to 0. Well, if TSP is equal to 0, right, then our Hamiltonian becomes very simple. Here we have the band structure of the s orbitals and the band structure of the p orbitals, and they don't talk to each other. These diagonal matrix elements are 0. Right? So we get two bands. One is an s-like band. Or sorry, let's talk about the band. One is a p-like band, right? Shown up here. This is the px orbitals that we talked about in the previous video, right? And they start at a high energy and they go downhill. And they have a bandwidth of 4 times that p transfer integral. And we have an s-like band. In fact, it's not s-like, it is just an s band. There's only s orbitals in here, and it runs uphill, right? And it's all these s orbitals that start together in phase at the gamma point, or k equal to 0, and at pi over a, each one is out of phase with its nearest neighbor. Okay, so that's pretty boring. That's something we've already seen in the previous 2 videos. Okay? And what we're showing here, I'm actually going to tell you what these parameters are. These are EP and ES. These are I just sort of chose these randomly. I chose this to be -5 electron volts, and this is 2 electron volts. And our transfer integrals are 2 for the s orbitals, 1 electron volt for the p orbitals. And these are ballpark numbers. They're not chosen from any specific model system. They're just giving you a flavor. The main point that I want to point out is we have our s orbitals are lower in energy than our p orbitals, and the 2 don't cross. Okay, great. All right. So if that transfer TSP is non-zero, so our s orbitals and our px orbital on nearing neighbors can mix, they're going to mix more as TSP increases. But let's start looking at the Brillouin zone boundary edges, right? So if I have 0 crystal momentum, k is equal to 0. When I go up here, well, sine of 0 is 0, so then the 2 don't mix. So I have pure s and p orbitals at k equal to 0. And if I look at k equal to pi over a, so the Brillouin zone edge, well, sine of pi is also 0. So I have pure p and s orbitals at the Brillouin zone edge as well. Okay? And so what's going to happen is that as I increase TSP, that transfer integral, I'm going to change where my minimum and maxima are, but at the edge of the Brillouin zones, I'm still going to have just s and p orbitals. Right? So we're not going to mix at the zone edges. And as we go along in wave vector, the s band and the p band are going to effectively repel each other. So the p orbital, so the p-like band's now going to have some s component in it. It's going to go a little bit higher. And the s-like orbitals, or the s-like band, going to have some p character in it, and it's going to get lower in energy. Right? So the 2 are going to repel. Okay? And in the limit, the 2 bands interact strongly. This is kind of a silly limit for most real physical systems, but let's go ahead and take a look at it so we know what we're dealing with. In the limit, the TSP is a large number. It is larger than T sub s, and it's larger than T sub p, right? So the s orbital here and the p orbital, px orbital here are interacting more strongly than either 2 s orbitals or 2 p orbitals. Then we can approximate that TSP is much larger than TS or TP, so we can just ignore those two terms. And we're going to get something that's going to look like, our wave functions are going to end up looking like even contributions of s and p orbitals in the middle of the Brion zone, right? Because effectively this is going to look like it's infinite. This is going to look like it's minus infinite times I. And so they're going to add together like this. An s orbital plus or minus IPX. Okay? But if we want to see what it looks like in the middle, I made a little video. And so this is the same parameters for the s and the p orbitals. I've just drawn them on a slightly different scale. So we have our s orbital down here, our p orbital up here. And now what's going to happen is we play this video, our transfer integral between the s and the p orbital is going to increase. And so watch what happens to these bands. Let's play this video. And you can see that the levels start to repel each other. This gets lower, and eventually this would be all the way down here and look almost symmetric if TSP went infinite. And this level repels. And we get the most mixing between the s and the px orbitals somewhere in the middle between k equals 0 and k equals pi over a. Okay. And it's going to tend towards k equals pi over 2. Over 2a, sorry. There's a wavelength of twice the length of the Brion zone. Let's take a look at what some of these wave vectors look like. We've seen several of these plots before, so let's go ahead and take a look at this. We have our real wave function, our imaginary part of the wave function, our density, and then our band structure. And we're going to show this for 3 different values of our transfer integral TSP. So how much the s and the p orbitals mix. Right, so let's play this. All right. We're playing, we're going forward. And what I want you to notice is that we're getting some p-like character, and that p-like character is showing up primarily in the imaginary component. If we actually go back here in our Hamiltonian, right, our mixing is purely imaginary. Now this is going to get multiplied by a plane wave that has a real and imaginary component, so some of that's going to come back in to the real part of the wave function. But as we look, we have this looks like the same at k equals 0. We start with an s-like orbital. We're looking at the lowest energy band here. Sorry, just looking at the lowest energy band. And this starts off looking just like s orbitals. In the middle, looks like maybe there's some p orbital character to it. And then as we continue to increase k, that goes away, and we're left with pure s-like orbitals. Okay. All right, now let's do it at our largest value for TSP. This is going to be TSP is equal to 5. And we're going to see something similar again. It starts at pure S-like, and then as we get over here, we're sort of in the mid, getting close to the middle of the Brion zone. We have some P-like character, right? We have these nodes that are occurring in the middle of our atoms, right? And so that's some PX-like character coming into our orbitals. And let's keep going for a second. And you can see this pretty clearly in the density there, right? So if we look over here, notice in our density, it even looks px-like, right? We see that we're starting to get these dips right in the center of our atoms, which is what we expect for px orbitals. This doesn't happen for s orbitals. Remember, s orbitals are spherically symmetric. But now, as we keep going along in k, we're going to return to our pure s orbitals. And our density is going to look like the pure s orbital, right? So even at large values of mixing at the Brion zone boundary edges, we still have our pure s and p orbitals. Okay, let's take a look again at just our wave vector having the wavelength of a 4-unit cell. So we're going to go positive, 0, negative 0, positive 0, negative 0 is going to be our phase factor. And what we're doing is we're increasing TSP, our transfer integral, our mixing between our s and px orbitals as we go down this table, right? So 0, this is what we saw on the very first video. Now we have some transfer, now we have some component of the p orbitals mixed in. And then as we increase our px, our sp mixing, right, then we have something that looks much more like an sp orbital in the middle of our Brion zone. It looks like an sp, it looks like an sp orbital, right? We have some s component and some p component in our orbitals. Okay? So we're allowing our orbitals to mix. I just want to make one comment about this. What we did here was we did this for just 2 orbitals. If we wanted to have more orbitals, we can pretty easily extend this. We just need to know more transfer integrals. But we talked about this in the atomic case. It doesn't need to be confined to the atomic case. We could use this with molecular orbitals. Let's imagine that we had some molecule, and we calculated the molecular orbitals. We had some set of molecular orbitals that we were interested in, and we then wanted to know, well, when I put these into a crystal, how do these orbitals interact, and what is my resulting band structure? So this is a paper that was written by our department. So this was by Professor Chris Douglas, Professor Dan Frisbee, and then Professor Jean-Luc Breda. This is some of the theory components. This is a paper, Professor Breda, not in our department. But this was a paper on rubrene, so molecules that have the sort of basic structure shown on the left that have individual chemical substitutions. And those chemical substitutions change the energy level of the different orbitals, right? So we have some electron withdrawing groups and some electron adding groups. And the details here aren't that important. But we can use those molecular orbitals, calculate a hopping integral or transfer integral for each of those systems. So this is looking at just the tetracene core. These molecules have 4 aromatic rings fused together. And based on the symmetry of how those orbitals add together, just like we saw for the s and the px orbital, we can estimate what that transfer integral is, and then we can calculate these band structures. So these are band structures for different rubrines, rubrine 1, 2, 1, 5, 6, and 7. Those are these molecules, A, B, C, and D. And we have valence bands and conduction bands. We have a variety of different bands. We're looking at more than one band per molecule, but it's the exact same set of principles that we used to look at the atomic sp chain. Now we're looking from gamma, x to gamma. We're looking along different paths in the Brion. This should be an x over here, I think, but it's individual lines in our Brion zone. Okay. All right, so we can use molecular orbitals as well as atomic orbitals, and what's going to determine the sign of those transfer integrals is whether they add together, whether one orbital and its nearest neighbor add together in phase or out of phase. Okay. That's kind of cool that we can extend that. And so that's how we're going to add multiple orbitals per unit cell. In the next video, we're going to talk about how to extend this to higher dimensions. So everything we've talked about so far has been one dimension, where we have block waves that move either forwards or backwards. And so this video is a little bit fast, but here's a square array of atoms with px orbitals. And what we're going to do is we're going to change, in this video, we're going to change our wave vector and allow it to move around. But now we can move to the left, to the right, up, and down. So we're going to get plane waves that move in different directions. And so we're going to see what that looks like. This video goes a little fast. It's just a tease. Right? But you can see that as we make a loop around the Brion zone, play that one more time, we get plane waves that move in different directions. So we're going to talk about that on our next video. I hope you enjoyed this video. If you did, please like and subscribe to the channel, and I will see you next time.